Hey guys, in today's video we're going to talk about real gases, and we're going to be looking at what a real gas is and how it deviates from an ideal gas and why that deviation occurs. We should be able to explain it in terms of intermolecular attractions and molecular volume, the reason why these deviations are occurring, and then we should be able to look at our van der Waals constants, A and B, and look at the trends within them and use our van der Waals equation to solve for our different variables within a real gas. So if we have an ideal gas is going to obey the tenets of our kinetic molecular theory. So ideal gases obey the kinetic molecular theory of gases. Remember, KMT, kinetic molecular theory. So, remember, in our kinetic molecular theory, gases, the particles themselves don't occupy any volume. All our collisions are elastic. There are no attractive or repulsive forces, those type of things. Now, if we have a gas at very low pressures or high temperatures, they will behave ideally. So when we're talking about low pressures, we're talking about low concentrations. And at high temperatures, we're talking about things that are going to collide and then keep going. So they're moving very, very fast. So we see over here in this picture, we've got a gas particle, it hits this wall, and then it hits another particle, and it just keeps going. So it's got enough energy that when it hits something, it's just going to keep on going and not do anything. And then if we're at low pressure, we've got things that are not very close to each other. Our gas particles are further away from each other. But as we increase pressure and we lower temperature, some things happen. So with ideal gases, we assume the gas particles occupy no volume. We assume that there are no attractive and repulsive forces. And that all collisions are entirely elastic. Now, when we compare this to a real gas, a gas where we have high pressures or low temperatures, now we've got things that are interacting more. As we get higher pressures, our particles are getting closer and closer together. As we get lower temperatures, they're not moving as quickly, so we don't have quite those elastic collisions that we see at the high temperatures. So when we decrease that pressure or we increase that temperature, then when we increase that pressure or decrease that temperature, what we see is things that are closer together interacting more. So in a real gas, and this is when temperatures are lower and pressures are higher, the particles interact more. And what this means is we don't need to have elastic collisions. We don't have no interaction, no attractive or repulsive forces going on. So now there are attractive and repulsive forces. because now that they're moving slower and now that they're closer together, they're going to have enough time to actually interact with each other. And we know that there are attractive and repulsive forces, or we could not condense a gas into a liquid, right? So they have to be able to exist in some way, some fashion. But in the case of the ideal gas, where we've got really, really high temperatures, really, really low pressures, we're not able to condense into that liquid, so we kind of assume that there are no attractive and repulsive forces. But now, with our real gas, we do have those attractive and repulsive forces, and we have collisions that are not quite elastic or as forceful. So the collisions are not as forceful, and they are not quite elastic. Okay? So both of these are going to result in a pressure that is actually less than expected. So the gas pressure is less than we would expect it to be. And of course, since we have things that are moving slower and they're in closer proximity, we actually have to take into account the volume of those gas particles. So slower moving, closer together particles. In this case, can't ignore the gas particle volume. So our volume will be slightly higher than our ideal gas law predicts. And we can look at this effect of pressure and temperature on our gas behavior through these following graphs. So the top one, we're looking at pressure and how pressure is going to affect ideality. So right here on this line is how an ideal gas will behave. And then we look at the pressure for actual gases. So the variation is basically showing as we increase that pressure, how much a gas is going to vary from ideal behavior. And we see when we are at less than 1 atmosphere, our gas is going to behave ideally. But as soon as you get away from that 1 atmosphere, you're going to vary sometimes wildly from that ideal behavior. We can also see that when we look at pressure and temperature versus ideal behavior. Here we've got our pressures, and then if we have a very, very high temperature gas, we can maintain ideality up to like 50 atmospheres. But at 200 Kelvin, we are nowhere close to ideal behavior. So how do we account for this decrease in pressure and increase in volume? We are going to use what's called the van der Waals equation. So our van der Waals equation takes into account how a real gas behaves. So this is a real gas equation. Okay, so because we have lower pressures and higher volumes, both of those terms, the pressure term and the volume term, are going to be changed in our van der Waals equation. So our van der Waals equation itself, for pressure, we have N squared, where N is our moles, times by A, and A is a constant, divided by volume squared. So we're going to add a term to account for the lower pressure, and then volume minus NB, where again, N is our number of moles, and then B is also a constant. Both of these constants are going to be dependent upon the gas. I'll talk about them in just a minute. And then this is going to be equal to just nRT. So we're going to change our pressure and our volume term in this case. Okay. Now, our A constant and our B constant, like I said, are going to be based on the gas itself. Here is a table of van der Waals constants for gas molecules. So let's look at our A term and B term. Our A term, as we can see from this chart, is going to have a very interesting unit. And that's because when we put it into this, we want to be left with atmospheres, right? So we want our moles to cancel out, our moles squared to cancel out, and we want our liters squared to cancel out. And then when we're using our B term, we want to be left with just liters. So since we're multiplying it by moles, we need to cancel out those moles. So you have some really weird units with A and B terms, but they're just there in order to cancel out units. Now, let's actually look at what our A and B terms mean. So our A term kind of talks about the attractive forces or the polarizability of the substance. So things that are going to be, things that have large A terms are either going to be polar or they have a lot of electrons that they can push around. So if we look here at our A terms, we see that things like water have large A terms, which makes sense because water is going to be a polar substance. NH3, another polar substance, also has a large A term. But we look at things like Cl2 and CCl4, those also have very large A terms, despite the fact that they are nonpolar. And the reason for this is because these are fairly large molecules and they have a lot of electrons, and because of that they can polarize those electrons, and then they can make the electrons go in one direction or another to get more attractive and repulsive forces going on. So it just has to do with how much attraction or repulsion we see. So really large substances with lots of electrons usually have large A terms, and then things that are polar. You can also see it with xenon. Xenon's a very polarizable substance because it has lots of electrons. Our B term is really just talking about size. So the larger the substance, the greater that B term is, because we're using this in our volume. So again, if we look, CCl4, again, has a very large B term because it's a very large molecule. Some other ones that are going to be larger are things like Cl2, right, and xenon. So things, again, that are larger molecules. So those larger molecules are going to have large B terms. Okay, so let's actually try using the real gas law in a problem. So we want to know what the pressure So what is the pressure of 2.00 moles of carbon dioxide at 298 Kelvin in a 5.00 liter container, assuming real gas behavior? So when we are doing something like this, we are going to want to look in our chart and see what our A and B terms for carbon dioxide are. So if we look up here, we see carbon dioxide right here has an A term of 3.59, and a B term of 0.0427. Okay, so we're going to put those values down. So our A term for carbon dioxide is 3.52 liters squared times by atmospheres over moles squared. And then our B term is 0.0427 liters over moles. Okay, and now it's just a question of plugging and chugging. So we have pressure plus our number of moles, 2.00 moles, squared, times by our A term, 3.52 liters squared, times by atmospheres over moles squared, divided by our volume, 5.00 liters, and square that as well. Then we take our volume term, 5.00 liters, minus our moles, 2.00 moles, times by our B term, 0.0427 liters over moles, is equal to 2.00 moles times by our gas constant, 0.08206 liters times by atmospheres over moles times by Kelvin, and then times by our temperature, 298 Kelvin. Okay, I want you guys to try this math out. Make sure you put it in your calculator. At the end, you should get a pressure equal to 9.38 atmospheres. Okay? So, the steps you should take, in my opinion, solve for this first, and then divide by the value you get here. And then all you'll need to do is subtract by the term you get here. So maybe solve for each one of these separately, and then divide, then subtract, and then you should get 9.38. That is everything. This is the very last lecture. I will see you guys later. Bye.